It's Michael?
Yes.
Yeah. Nice to say your mask off now.
Right.
Hey, Khalid. Hey. Yeah.
Hi, how's it going?
Good.
Yeah.
How's it going, Jordan?
Good. Just enjoying the morning apple.
Yeah. It's actually afternoon here. Almost
yeah.
6 p.m. Yeah.
Oh,
Yeah.
well, an afternoon apple then.
Yeah. Afternoon coffee here.
Oh, 6 p.m. coffee. You're an all
Yeah,
day
yeah.
coffee,
Somehow, you know,
all day coffee guy?
after midday, you know.
Yeah.
Yeah. You know, it's like 8 hours difference between here in Saudi Arabia and Chicago time zone, you know.
Yeah.
So
Gotcha.
whenever you are like 9 p.m., 9 a.m., we are here in 5 a.m., 5 p.m., I'm sorry.
Yeah.
It's the afternoon. So we are 8 hours ahead, you know.
So if you take a 4 o'clock class, you will be there at what, midnight?
Yeah, yeah. I think you are familiar with that because I think it's 3 hours difference between Saudi Arabia and West India.
Probably, yeah. Actually, India has a common
Yeah.
time zone everywhere, yeah.
Yeah.
So are you in touch with your friends here? So you got used to this time zone?
Yeah, yeah. I keep it in mind, you know, when I was in US, I keep it in mind to call my family and everything. Yeah. I always keep it in mind, so, you know.
So Moses, you decided to prefer online now, is that?
Today I just
oh, yeah. Now there is a choice, right? You wake up late and you can.
Yeah, I didn't get going very quickly this morning, so.
Oh, so Alia is also online now. Okay, everyone is online now. Only Luke is here. So there's only one of us here. Luke is here. I think you guys cannot see him. Yeah, it's too much to move that camera all the way slowly. Okay,
Good morning.
So what? Morning, Alia. So 1, 2. 5 and 6. Yeah, so we are all of us, I guess.
Sorry, you're the only one in the classroom.
Yeah, I think at this rate, within a few days, it will be just me. Surely good for social distancing, I suppose. Yeah, not sure about. How do you guys like it when you're across the online platform? Like virtual learning, Luke? Like, would you like between when you're across on a virtually, is this any significant difference?
I'm not sure.
Okay.
The classes in my semester, in my undergrad, most of them didn't seem to be much difference, but
It's not much difference. Yeah. What about Michael? What do you say?
This is my first online course, so
Oh,
I'm not sure yet.
okay. Yeah. Alia, do you have any preference?
No,
No. Okay.
I'm okay.
Yeah. Nice. Yeah.
No, which one is your teacher?
There is a certain
Okay.
convenience, I guess. Now that we've kind of had this amount of time to get used to, online learning and just having Zoom meetings and Zoom classes and stuff. I guess, like the convenience of not having to go anywhere is, I think, probably the biggest thing for me. I imagine that would be true for you as well, particularly like coming into the classroom and setting everything up, as you were mentioning.
Yeah, true. But I would say that the physical interaction is significantly better.
It's superior. I agree.
Yeah. I think the two-dimensional thing does not capture a lot of features. I cannot explain it. It's I tried explaining this better, but I never could articulate it. But I can sense the difference very strongly.
Yeah.
for me, my classes were really brief last semester, so in general, it was kind of the same effect. There wasn't a lot of like.
Makes sense.
Yeah.
Yeah. For a big classroom, for example, in an auditorium, anyway, you don't have an interaction. Here, I think it could be as simple as looking into someone's eyes or something like that. Like there is a lot of more emotions that goes into some local interaction or abroad. And I try to relate it with sometimes if you break your hand, only then you realize how much you miss it, kind of. So it's something like that. It's hard to explain on a normal circumstance, but surely at least from my perspective.
One of my friend he's doing PhD in linguistics, and he told me that many researchers there say that only 17%, 17, of the human communication by words, only by talking.
Yeah.
The rest of that is by body gestures, eyes, and facial expressions, and everything. That was amazing.
Yeah, that's good to know. Yeah, I never put a number to it, but yeah, that's related to what I'm trying to point out. I think so. But I understand the safety requirement also. So that's a bargain we have to make, and it's hard to make that bargain. That's the toughest part.
Yeah, here in Saudi Arabia, they made a decision that the first 2 months of the semester should be online for all the education levels, from elementary school to the
college,
to the university. Yeah.
Okay.
Yeah. So
that surely gives time. Yeah. Okay. Well. Yeah. let's see how it goes here. Yeah. Yeah. Okay, so about the course, again, I cannot pass on the syllabus. I think all of us were there yesterday also, right? All of you guys are there in yesterday's course also. So that's, so I don't have to introduce myself again. The website remains the same. I'll write it down anyway. That's spherical harmonics .com, and you should be able to click on a different course this time. Yesterday it was E&M. This time it's math methods, and you should be able to get a syllabus, and there's a homework also. So Jordan, I did fix the homework part yesterday, and I also noticed that you already submitted the extra credit thing. So so it seems to be working that way. So again, remember that there are the distribution of the grades is exactly like the other one. Let me quickly go over it. So it's homework, 40% is extra credit. No, that's not correct, right?
Yeah, 5%.
It
Yeah.
was 30% yesterday.
30, because there's this
30,
another, yeah, because I'm working for another course. That this is a big jumbo classroom that I'm going to be teaching in 2 hours. So my head is in that, I guess. Yeah. Okay. So what else? So it's midterm exams. That's 45, and final exam is 20. So this distribution is entirely different. The other one. Is my volume any better today? Because I'm using a mic today over yesterday, because I tried to listen to myself and I couldn't understand myself. So hopefully it is slightly better. If not, I cannot do much.
yeah.
I'm sure. It sounds pretty good, but I heard you fine yesterday as well. So
Okay. Okay. Then maybe it's I don't understand myself. Okay. Okay. So usually, most of it is the same homework. The only thing I will stress again is that extra credit. I noticed that Jordan already submitted this, so this is very easy. You just go back and if I were in place of a student, I would try to remember immediately after the class. So I'll do it on the same day so that it's clear where I spoke what. So you have to go through the lectures or lecture notes, just mark where the extra credit problem was, and try to think about it for 5 minutes and just answer anything that comes to your mind immediately. Preferably, or the hope is that it is exciting enough that you search it up a little, but just the thought is also sufficient enough. The idea is to have some sort of discipline as to you're doing the work, and I think motivation is here is that, okay, you open your book and then you tend to work. It's like a inertia issue. So that, yes, please.
about the submission online, as I noticed, after you submit it, you can't actually, it sends you an email to tell you submitted something, but it's kind of nice when you submit something to be able to see what you submitted. I tried to see, like, because a lot of times you submit something but you either didn't actually submit the right thing, or so it's nice to be able to like download your own link to make sure that you actually submitted it outside of it just saying you submitted something, because sometimes it just submits nothing. And then
Okay, that's good to know. So you like the feature?
Yeah, I like being able to like actually see that, hey, you submitted, if I named it assignment 5, and I can click on it and it pulls up the little PDF of it and said, okay, yeah, it's actually here, instead of it just.
Perfect. Okay, that's good to know.
Not that big of a deal.
Also, there was an option when I was setting it up. It asked me, can you replace the file? So I did allow you guys to. So you, like you submitted it right on the first day, and 2 days down the line you felt that, oh, I don't like it, I want to change it, you can actually change it. Or at least I put the settings there, I intended to do that. Now let me know if it is not
And
working.
it also helps when you submit PDFs because, like, say I have saved on my phone from taking the picture, the PDF picture, like 10 extra credit assignments between the two classes, and I accidentally click on number 9 for this class instead of number 9 for the other class.
Yeah.
And I see.
Yeah, happens. Yeah, sure. So that's good to know. Yeah. So, and even the homeworks, I'm planning to make it, or at least I'll have that option, because at least one of you guys cannot fly every week, I suppose, to submit your homework. So Khaled has to do it online. So maybe as well put that feature for everyone. I like to have a physical copy. That's different. It's just convenience, but I can live by. So choose your option. It's okay with me either way. Okay. So for example, if you're not coming to the classroom on that day, as well do it online. Okay. And if I find it very inconvenient, then I'll get back to you guys. Okay. So yes. So again, the point is extra credit does change your grade significantly. So don't miss on it. So I'm especially for those of you who have not been in my classroom, after a certain stage, it might be late to get back whatever points it is. And it is very easy. Remember, it's a participation point. I don't assess the correctness of the submission. It's just submission that matters. Something should be there. Even if you don't have anything to say, oh, I searched, I didn't find anything, that's also a good enough submission. It's just that you did something. That's what it is. So let me not go over the details. Everything stays the same. Curve, everything, exam. So there is a homework one. Oh. So that's where the line ends. Okay. So homework 1 is due. I made it due in a week. So that's August 25. That's Tuesday. Hopefully I can finish everything. And midterm is way away, September 10. I think I did mention this in the other class also. The exams will be in the classroom, so that's not optional. So you have to be physically present in the classroom. So Jordan, you will have to drive on that day, I suppose, unless I decide to do it, do a take-home exam. I haven't decided. Do it pretty often, give take-home exams, but by default it is going to be in the classroom. So be prepared for that. You shouldn't have any issues with that. I might decide to have it take home maybe a few days, surely within 3 or 4 days before I will know whether it is going to be take home or not. And Khaled, we should talk about how you will manage. Obviously, you cannot come to the classroom. Yeah.
Sure.
Yeah. Okay, so I think that's a reasonable summary of So usually this course runs parallelly to the E&M, and E&M requires you to have a good handle of vector calculus. Of course, most of you probably have done vectors to a good extent, but vector calculus often you're not very fluent on it. And yesterday I pointed out about what a gradient operator, I mean, we should have a feel for what a gradient operator is, irrespective of the coordinates itself. So that's what we would aim for. So so the first homework or first couple of weeks, we are going to be doing vector calculus mostly, and also curvilinear coordinates. So that's what is going to be the first 2 or 3 weeks, let us say. This is mostly used in areas of, if we go in an advanced level, general relativity, which probably you have, most of you have come across. What is general relativity, by the way? How do you, what comes to your mind when I say general relativity? Curved space-time, yeah, Einstein's work of understanding gravity, which generalizes the work of Newton. So it's a significant work that pretty much involves what is more broadly called differential geometry, but at a very simplistic level, it is curvilinear geometry. So yeah, curved space-time is a good way of saying. So if the space is, if you're using curved coordinates or geometries that are curved, then how do you describe it using coordinate systems? So introductory level of that, that's what we will cover in there, but not in the context of gravity itself, but in a more general setup where we can make it useful. That's going to be the first 3 weeks. So yeah, that's a good thing to summarize, right? So first we will do vector calculus. And let's say curvilinear coordinates. So that's probably 2 or 3 weeks. Second is we will do analytic function or complex functions, let's say. What do you understand by complex functions? Anyone again?
A map from the complex plane to the complex plane.
To the complex plane. That's a reasonably good way of visualizing it. And we also want to talk about continuous. Basically, we want to talk about differentiation and integration on a complex plane, and that leads to very nice concepts, what is called Cauchy's theorem, and so on. So that's something we'll do again. We'll try to do it to a certain extent, not to too much detail, but at the same time, reasonably introductory level, so that you can take it off on your own from that point. So about 2 or 3 weeks on that. And the main part of the course will be differential equations, but in the context of Green's functions. So usually we learn a homogeneous differential equation, but this time we want to talk about inhomogeneous differential equation. That means on the right-hand side, you have a source sitting there, and the right technique to deal with that is the Green's function. So this is differential equations. And if time permits, we'll do spherical harmonics. And perturbation techniques. Usually I've seen that it's just possible only to reach spherical harmonics barely in a week or so. So that's probably what we'll be dealing with. And we'll start with vector calculus. So let's do vectors to begin with. Right? Let's say vector algebra. And in this context, we also want to talk about what is known as index notation. So some keywords maybe, just so that you can, what are the topics we are dealing with? What is index notation? And also dyadic notation.
Can you move the board?
Oh. How's this?
That's good.
Is it still readable?
Yeah, it's still readable. Yeah.
So I think I zoomed in too much here. Okay. How many of you have heard of what is index notation? It is not a very popular topic, so don't feel, if you've not heard it, that's okay. What is index notation? Anyone? Anyone who has heard
easier,
it?
basically. Yeah.
Tell it again.
It just makes stuff easier to do. Like,
Yes, that's correct. So you have heard of index notation. Luke, okay. Michael, have you heard of index notation? It's okay if you're not heard. It's not common.
It sounds very familiar, like matrices.
That's correct. Yeah, that's roughly related to the idea of matrices and all, array and matrices. Yeah, good. Okay. So that's what and it's very similar notation is what is called dyadic notation. And often I've noticed that in my courses, at least, I switch between the two. Often as a student, index notation, as a mechanical work, index notations are easier, but sometimes when you want to have a visual picture of what is going on, dyadic notation is useful. Probably everyone likes their own way, but it's just a matter of convenience here. There is nothing deep in here. So whatever we are going to be doing is more of a bookkeeping process, which helps you in dealing with complicated stuff, but conceptually nothing significant. So that's one thing you want to keep in mind if you're getting overwhelmed with what's going on. So it's a rule. It's just a rule. Often, again, from my experience with students, students get thrown away from what is going on. But this is a set of rules, and as it is a set of rules, you just have to make sure you understand it. If you don't understand it, ask your friends or me, just come to me. And once you pick up the rule, it is very powerful. So, and it's not just used in my courses. It's very useful in general, even if you're doing computer programming, that's a good idea to have. So think of it as a rule and try to learn it. Contact me. Often it is harder to read through a set of rules. And for some reason, there is no one good reference for this. One would have thought that these are a set of rules. So there is one nice textbook that has done it. So there is no such one good textbook, but there is a lot of resources out there, but nothing good enough that I can actually give a pointer, and you guys can go there. So look it up, or else I'll try to teach whatever it is worth. Okay, so what is vector algebra? So let's think of it as two vectors, vector A and vector B. Like it's clear that when you put an arrow mark, that is a vector. A vector is different from a scalar in the sense that it has a direction also associated with it, and there will be more better definitions one can give for a vector, but for our purposes, it is sufficient to see that it is actually something with a direction. And what do you mean by direction? If you're in 2 dimensions, it's very clear that it's an angle, right? So what do we mean by a direction, correct? So if you're in 2 dimensions, so the length of this arrow is what is the magnitude, And now in direction, this arrow can be anywhere on this plane, and a very unique way of saying in what direction that points is to give an angle with respect to a line, right? So you need to first have a x direction. This could be, need not be x, any particular direction. With respect to that, you have to say an angle. Usually I say, if you're talking on phone and you want to tell someone that you want to go in certain direction, you have to use this language, right? You cannot use your hand to point out in a certain direction. If you're physically present, you say that, oh, you go in that direction. But if you're talking on phone, you have to use this language. First, you will give a reference point, and then you will say, oh, certain angle, or look in the certain amount of angle in the other way. So that's what direction means. So theta is, so this length, let's say, so this is, this could be, this is A, right? So A is the length of this vector. Usually you say this is the magnitude, and theta is the direction. That's good enough. But what if you're in three dimensions? If you're in 3 dimensions, how do you give the direction? How would you give the direction in 3 dimensions?
Components.
Tell that again.
Components.
Oh, yes, good enough. But again, okay, good point. Okay.
Angle, I guess.
Tell that again, Jordan.
Add another angle.
Yeah, add another angle. I think that was the answer I was looking for, but the components is also a good answer. So let's go back to this. So the correct answer, or what I was looking for, there is no correct answer here. I was that as another angle in here. But let's go back and look at this. So notice, even in 2 dimensions, there is this x component and y component, correct? So there is x component here, there is a y component in there, right? So in principle, if you want, a vector is uniquely represented in terms of the x and y components, or for that matter, even using a magnitude and direction, right? This is also another representation. So that's A. Notice when I don't put the arrow mark on it, that means it's the length of the vector. So that's the magnitude of the vector, and angle theta. And then let's say, just to clarify that this is actually the magnitude and direction, so let's put a colon instead of that. Now there are 2, at least there are 2 representations of a vector. What's the difference between the 2? So I said, like both are good answers, right? There is x and y. What is it that you gain by using magnitude and direction, and what do you gain by using x and y component, or is there any difference at all?
More coordinate systems, I guess. I don't know.
No.
AX, AY is limited to just one coordinate system.
Yeah, but something that you can do in this, but in principle it can be done in this, but it's very easy to do in this.
Like adding up vectors and subtracting them.
That's very good answer. Notice adding and subtracting you can do very easily using components. But if I were to give you the magnitude of 2 vectors and directions of 2 vectors and ask you guys to add them, it is harder. Basically, you have to use the cosine law and bring in all the trigonometry in there. So what usually you do is that algebra is done in this representation, but visual understanding happens in this representation. You have a very good insight into magnitude and direction. But when it comes to algebra, if you want to add or subtract, you go to this. So you keep switching between the 2. And what's the connection between the 2? So the magnitude A is ax square plus ay square. So that's your, and angle theta is tan inverse of AY over AX. One has to be careful about which region you're in. So this is multi-valued. So one has to be careful whether you're in one quadrant or the other. There is small confusion or ambiguity in there, but usually, at least in two-dimensional pictures, it is not very hard to figure it out. If it's the other way, if you're in the components and you want to write the other way, I think I can squeeze in 2 more lines there. AX is equal to A cosine theta, and AY is equal to A sine theta. Is that still visible? Is that readable? Yeah. Okay. So the question was, how do you generalize this to 3 dimensions? That's 2 dimension and 3 dimensions. These coordinate systems generalize very nicely, right? So if you're in 3 dimensions, this simply becomes AX, AY, AZ. Right? You just add on to the third components, addition, subtraction, everything goes through smoothly, right? That was what probably Jordan had in mind when he was saying, I think coordinate system you can put in higher dimensions. What about magnitude and directions? And again, I think some of you pointed out that you again put a magnitude, and direction now doesn't come with 1 angle, it comes with 2 angles. Right? Think of a sphere. If you're on the surface of the earth and you are sitting at the center of the earth and you want to point in some direction on the surface of the earth, you need 2 angles, correct? One is a latitude and one is a longitude. That serves the job. Or think of looking into the sky. You want to actually mark a star, right? You need 2 angles. You would say that, oh, first let's put the North Star, and then with respect to that, how much angle. So two angles in astronomy, you don't usually use latitude and longitude, or at least I think you don't use latitude and longitude. You go with respect to the North Star. I'm not sure though. Okay, and yeah, that's a good exercise, right? Extra credit, right? In astronomy, if you have to point at a star, I'm sure you will give 2 information. What are those 2 information? Are they the same? Are they related to latitude and longitude, or not? Okay, so that's the question. So surely North Star plays a role. That's the North Pole if you want. So there is a 0 angle, and with respect to that, you make the measurements. So look up what are the quantities that comes into that. So if you are in spherical coordinates, you would say this is theta, and there is another angle, that's angle phi. So that's what you would you do. So that's the idea. But now we want to be able to do standard algebra. So addition is easy, right? So here is the, so this is index notation. Index. So a vector A has 3 components: AX, AY, AZ. If you're in 3 dimensions, but when you work in terms of components, you can easily go from 2 or 3. It doesn't matter. We have already assumed that we are in the rectangular coordinate system, so we have made a lot of assumptions in there. A vector, in principle, doesn't require a coordinate system to be specified. It has an identity of itself, but we are in that regime where we are talking in terms of rectangular coordinates, right? Instead of saying x, y, z, you would say this is equal to just ai. Right, that's a notation now. So index notation comes into picture. So this is I is equal to 1, 2, and 3, with the understanding that 1 means x, 2 means y, and 3 means z. And if you are to put in space and time also, sometimes time is given 0 or sometimes it can be 4. That's also perfectly fine. But time has some different characteristics, which we won't get into at this point. Maybe some other time in another context, we might have something to say about it. Okay, so that's a simple, it cannot be any simpler, right? Just a notation there. So if you're adding two vectors, A plus B, this is as far as components goes. So this is, so let's say the components, right? So AI has become the components of the vector A plus B. So these are vectors and its components are simply AI plus B. Right? So the components add separately. And maybe I should specify this here. So these are components of vector A. So this language here means that this is the ith component of the vector A plus B. If you're doing subtraction, this is plus or minus, it becomes plus or minus, pretty straightforward. So no big deal. You would even say, why even call it an index notation? That's straightforward. I mean, everyone knew this right before. That's not where this is useful, but vector algebra doesn't just involve addition and subtraction. There are two more things you do with it. And one is A dotted with B, right? And the other is A crossed with B, right? So this is a dot product. And if I were to do this in 3 dimensions, there are 2 ways of doing this, correct? Again, there is a component method and a magnitude direction method, correct? So similarly, the dot product has 2 ways of writing this. You can say this is let's say A1, B1 plus A2, B2 plus A3, B3, right? That is how you would write your dot product, right, in rectangular. So this could also be X, AX, BX, AY, BY plus CY, BY. That's great. But now you say that, oh, that's 1, 2, and 3. I can write this as a sum of I going from 1 to 3, AI, BI, right? So that's something, some small compactness there. And this easily generalizes to higher dimensions. Notice in this course, we won't need it, but that's one of the motivations that even if you're in 11 dimensions, you can still work with it. The same notation works through, and you don't have to write so much. But now you take a small leap here. You get very lazy, and you say that that's not sufficiently simplified enough. You also want to avoid writing the sum. And that's where the simplification, if you want, happens. And that's also where this confusion begins. That now suddenly there is no summation. And you simply say this is AI, BI. But then how do you know that this is being subbed over? Like in this context, I told you that, oh, I went from this step to this step. But somewhere in between, if you come across two quantities with i's repeated, how do you know that this is being summed at all? So that's what is called the index notation. So index notation is there's an implicit in the sense you have not explicitly written, implicit sum over repeated index. Only if it is repeated. If it comes on its own, you don't sum it. For example, AI here, right? This is not repeated. Notice it should come in the same term. Plus is not repeated, right? This is these are two terms. In the same term, if it comes twice, then you say that it has to be summed. So that is an understanding that is a summation. So that's the idea. Okay, any questions on that? Okay, so that's as simple as that. But now we are going to exploit this. We are going to expand on this. Okay, so that's good enough. So that's your dot product. Let's at this point define a symbol if you want. So this is called Kronecker. I hope this is correct spelling. Kronecker. Okay, Kronecker delta symbol. I think that's what it's called. This will be defined as, so this is a quantity we are defining. This is I and J. Now, is there a summation on this?
No, because they're not repeated indices.
It's not repeated. So there are two indices here, I and a J, but it's not repeated. Okay. So now what is it? So that's just a symbol. So here is what this means. This means I can take 3 values, J can take 3 values. So it's a combination of 9 objects in a sense, or 9 components. A vector has 3 components. This has 9 components. Usually it is nice to write it as delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, 2, 2, 2, 3. Is that visible? Okay. So whenever you have indices, each of the index can take all the possible value. Since it's not summed over, it is that has 9 components, but this is just a symbol at this stage. But this is where this becomes an actual Kronecker delta symbol. The sense you associate this to be, this is actually an identity matrix. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. What that means is that delta 1, 1 is 1, delta 1, 2 is 0, delta 1, 3 is 0, and so on. So that's a mapping, if you want, between these quantities. Often you just say that delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. A lot of things happened here by just by me introducing this symbol. One is that I have introduced the idea of matrices, if you want. Later it will be called a tensor. This is having 2 indices, right? So keep that in mind. And second is, this is an identity matrix. Right? It does matter that to interpret this as an identity matrix is important. But again, just giving you this information, it should be straightforward. It's just a simple idea, Kronecker delta, and we have a dot product, right? So we have 2 independent things, but now I'm going to combine the 2, right? How a dot product involves a Kronecker delta. So now let's say, let me let me try to tell you so that somewhere in an equation, I write the following. Okay, I delta ij and bj, right? So the question is, what is that equal to? Okay. Notice that I is repeated. So that means our notation says that there is a sum. J is also repeated. So there is a sum on J also. Correct? So there are two sums in this. So immediately you say that, oh, this is implicit. This is equal to 1 to 3. And this is J is equal to 1 to 3. And this is AI. Clear? And let's explicitly write this just for the fun of it. Let's just to clear. We see this. Notice if I expand this, there will be 3 terms. If I expand this, there will be 3 terms. So overall, there are 9 terms in it. Right? That's a lot of terms in there, but let's just explicitly write it. Right? So first, let me expand J. So I'll keep I as it is and expand J. So this is a I delta I 1 B1 plus AI delta I 2 B2 plus AI delta I 3 B3. Right? Is that clear what I mean there? And now each of this term has an I repeated in it. There is a summation there. You have to expand that also. So each one you expand. So this means a 1 delta 1 1 P1 plus so let me write it at the bottom, right? So this is 2 delta 2 1 P1 and a 3 delta 3 1 P1, right? So I'm just collecting them as a matrix if you want. So this is a 1 1 2 P2 plus a 1 1 3 P3 plus and I purposely wrote it in a certain manner so that the pattern of the Kronecker delta shows up in there, and this basically can be written in the matrix form also. But remember, Kronecker delta has specific numbers associated with this. These 3 are 1, right? Delta 1 1 is 1, delta 2 2 1 is 1, delta 3 3 is 1. Rest of the 6 terms are 0, right? So this doesn't contribute, that doesn't contribute, that doesn't contribute, and so on. Right? So this whole thing is just equal to, since delta 1 1 is 1, so this is A1 B1 plus A2 B2 plus A3 B3, which is nothing but the dot product. So the summary is that you won't be going through all these details all the time. You don't want to go through all these details all the time. You should be able to look at this and have clearly in mind that this is dot product. That's the harder part. To get used to that notation is the harder part. And for some reason, there's a big jump students have to take to get used to that. But hopefully this helps. But we will, this is the easier part, we will do cross products very soon. But again, summary is that A dotted with B. So what you want to take home is that there are two ways of writing A dotted with B in index notation. One is simply AI, BI. That's good enough, right? I is repeated, so that means there is a sum, that's a dot product. Right? Or if you want, you can write that in terms of the Kronecker delta, then there are two indices. I don't know exactly what is the stumbling point in students, but maybe it is two indices. That's when they start getting confused. But at least in this example, in this context, it should come out straightforward. It's only when 2 weeks down the line, when many things have come together, probably the confusions begin. Any questions at this stage before we proceed on with more things? Okay. Okay. So that's dot product, but I said there is a cross product also, right? Oops. So let's remind ourselves of how do we take cross product of two vectors, correct? Let's say you're doing A crossed with B. Let me explicitly write this. Maybe this is A1. Oops, A1. Right, A1, and let's for a moment let me write it as I. This is I've not been using this, but I think these are the three unit vectors associated with the vectors, but irrespective of that, it can be written as three components, and your B is B1 plus B2 plus B3. And what is A cross B? Anyone remembers? What is A cross B?
You do the A2JB.
Oh, A2J. Where is J? Oh, A2J. Yeah, yeah. No J, right?
Yeah, no J. Yeah, just A2B3 minus A3B2.
Good. That's the I. And then let me write this as plus. Usually, sometimes we write this as this is A3 B1 minus is that correct?
Yep.
Okay. So 3 will be A1 B2 minus A2 B1. Is that correct? Can you guys see it? Does it go all the way here? I cannot see it.
Yes.
Okay. Notice a pattern here. This is the first component that has 2 and 3. This is the second component. So this is 1, 2, 3, right? So the first component involves 2 and 3, and then swap it. Second one involves 2 and then 3 and 1, right? Second one, 3, 1, swap it, right? And the next one is third component is 3, 1, 2, right? And then swap it again. So that's a pattern, and that motivates one to define a symbol exactly like Kronecker delta. This time it's called Lewis-Civita. Civita, I think. Symbol.
I think is that right?
E? Correct me. Yeah.
I think it's E.
E. Okay. Save it. Thank you. Thank you. Thank you. Okay. So what is Levi-Civita symbol? It is written as I, J, and K. Right? There's 3 indices. It's not repeated. Neither one of them is repeated. So how many? So there is no summation over any of these quantities. How many components does it have if you're in 3 dimensions?
27.
27, because I can take 3 values, J can take 3 values, K can take 3 values, 3 into 3 into 3, 27 components in there, and it gets hard to compile them. Right?
Also, it's I. I looked it up. You're right.
Oh, it is I. Okay.
Yep.
Thank you.
Don't listen to me.
Helps. No, helps to be in front of the computer, right? I wish while teaching you could have that feature also pretty quickly look it up. But thank you. Yeah. Small advantages of having online, right? You can pretty quickly look it up. Yeah. Okay. So Levi-Civita is you would say later on, I'll start using the word tensors is a 3rd rank tensor. Vector will be the 1st rank tensor. Like Kronecker delta is a 2nd rank tensor. This is an example of a 3rd rank tensor. But from our perspective, in the scale in which we will be working, these are just indices. 3 index quantities, that is sufficient. The idea, there is nothing deep in there. That's all I'm trying to suggest. Okay. So what is this? How do we first of all portray this? So let's have I set to 1, right? So since I can only write 2-dimensional, so let me set I equal to 1. Then I'll set I equal to 2. And then I'll set I equal to 3. When I set I equal to 1, J and K can take 9 values, right? 3 by 3. So that's 9 by 3 by 3 values. So that I can put it on a matrix kind of structure. And this is epsilon 1, 1, 1, epsilon 1, 1, 2, epsilon 1, 1, 3, right? 1, 2, 1. I think the pattern should be there. 1, 3, 2, 1, 3, 3. So if you want to think of it as a cube, this is the first layer of the cube. Cube can be thought of as 3 layers, 3-storied building, if you want, in the shape of a cube. Now I change, so I've kept I equal to 1 in all these. So now I just change that to 2, 1, 1, 2, 1, 2, 2, 1, 3. And the same thing here. I think I might go out of the camera at this stage, but you guys can visualize it. 3, 2, 1. Okay, that should be pretty straightforward. I just, for completeness, wrote down every term in there. But now I have to give a definition, right? This is just listing the components. I have not defined them yet. But now this is a rule. Earlier we had this rule that if I is equal to j, this is 1. If I is not equal to j, that's equal to 0. But now we are going to make this rule that so if any of this index repeats, right? So there's 1 repeats in this, right? 1, 1, 1, it's 3 actually. So this is 2, this is 2. if any of the index repeats, I'll set it to 0. It's the opposite of Kronecker delta. Kronecker delta was if I was equal to j, that is 1, and otherwise it is 0. In this case, it is the opposite. If it repeats, then I don't want it to survive, so it is 0, right? So this is equal to 0, 0, 0, 0, and this one I'll leave it open for now. Oh, that's also, oh, 2 repeats, that's 0. 1, 2, 3 doesn't repeat, right? So this is 0. This 1, 2, 3 doesn't repeat, that's 0. So there's 2 points that I've left open. Rest everything is 0. Right? And now comes, what do I give the values to that point as? Now I look into 1, 2, 3. Notice this is cyclic. 1, 2, 3. So what are the cyclic terms will be 1, 2, 3, 2, 3, 1, 3, 2, 1. So those are cyclic. If they're cyclic, I would say it is 1. What is non-cyclic is 1, 3, 2. Right? 3.
Excuse me, the third one is like 3, 1, 2.
Yes. Sorry. Thank you very much. Correct me when I do this mistakes. Thank you very much. Yeah. So the cyclic is 1, 2, 3, and then you keep going. So it's like saying 1, 2, 3, right? So if you're going clockwise, it is cyclic. If it is counterclockwise, it is negative sign you would put in. So all this will give you positive sign 3, 2. Did I say this correct? 3, 2, 1. Yes. And then let's say 1, 3, 2. So these are all counterclockwise. So how do I put this? So this is going to be 1, and that's minus 1. So I put a value of 1 here because that's cyclic. When I go 1, 3, 2, that's not cyclic, right? It's 1, 3, so that's counter. If you want, if this is one is clockwise and the other is counterclockwise, so that's how I put a minus 1 sign. What are the other terms? So this is 0, 0, 2, 1, 3, 2, 1, 3. I'm going, so that's minus 1, 0, 0, 0, 1, 2, 3. So that's 1, 0, 0.
So you have 2, 1, 1, 3, 2 terms instead of, you have 1, 3, 2, 3, 2, 1, 1, 3, 2. You're missing that third term.
This one here.
No, when you were defining your cyclic versus countercyclic terms, you have a 1, 3, 2 term, a 3, 2, 1 term, and then a 1, 3, 2 term again. I think you're supposed to have.
Yeah. So that should be something.
The 2 term.
Yeah, what is that?
2, 1, 3.
2, 1, 3, I guess. 2, 1, 3. Yeah, 2, 1, 3. Thank you. Yeah. So you start from 2. Yeah. Yeah, 1, 2, and 3. Yeah, correct. Right. Thank you. And there is this third for completeness. This is 0. This is 1, 2, 3. So that's 1, minus 1, 0, 0, 0. Again, just a definition, nothing deep about it. But so now, how do we define this? Once you have set this all up, this is equal to, you would say this is equal to 0 if for repeated. Index, this is equal to 1 for cyclic quantities, and that's minus 1 for anti-cycle. What do you say? Counterclockwise cyclic, right? What's the opposite of cyclic?
Anti-cyclic.
Anti-cyclic. Okay.
It's still cyclic, but it's the opposite direction.
Yeah, anti-cyclic. I was writing counter-cyclic because. But you get the point, right? Okay, so I said this has something to do with cross product. So how is this related to cross product? So let's see. So, so let's do epsilon I j k a j b k. Now this is the first thing I think. Okay, let me ask some questions here. There are how many? Okay, is this whole quantity, is this a vector? By vector, I mean there are how many free index in this? By free index, I mean something that is not summed.
Just one free index.
Just one. Is that clear? Because j gets summed over because that's repeated. K gets summed over. What is remaining is just I. Right? So this is in principle a vector. This has only 3 components. Even though it looks like there are what 1, 2, 3, 4, 5 indices here, there is only one free index. It's a vector. It's not a tensor of 5th rank. Like it's not 5 index means 3 raised to 5. That's not what is happening. Most of them are summed up, so it's only 3 index. So this should be a vector. What has 3 components? That's vector, right? So we expect this to be a vector. So let's see how this goes through. So immediately, this is summed over j, right? So this is j equal to 1 to 3, k equal to 1 to 3. Notice in the beginning, I'm writing this explicitly, writing the sum over. The idea is that very quickly, within the first homework or so, you should be able to jump a few steps and immediately see 3 steps down the line. Like most of this with practice should go away. Right? Expand this out again, correct? So this is equal to, but this time I'll get lazy because there are too many, right? 27 terms I would expand and write. If you allow me, I will use these features in there. Notice many of them are zeros. Like those 27 terms out there when I expand, correct? Most of them are zeros except 1, 2, 3, 4, 6 terms in there, correct? Only 6 terms are going to contribute. So so let me write it the following way. So let me ask what is 1 jk. So I've set I equal to 1. Right? I've set I equal to 1. Is that visible there? Yes. Aj bk. Okay. But if I set I equal to 1, j and k cannot take values of 1 because then it will be 0. So j and k has to be 2 or 3, and 2 and 3 can come in 2 different ways. So out of this whole sum, which again has 9 pieces, I'm going to say that this is only 2 pieces. So 2, 3, A2, B3, plus epsilon 1, 3, 2, A3, B2. Is that argument clear? Any questions in there? I jumped a lot of steps. Instead of writing 27 terms and then setting it to 0 and going through, I've actually identified that only 2 of them survive, and those are those 2 terms. Okay, is that clear? Once you have this, you say that, oh, that's cyclic, so that's 1. Right, that's A2, B3. That's minus 1. That's minus A3, B2. Okay. And if you match it with the x component of A cross B, that's exactly that. That seems to suggest that, oh, whatever we have written here like this seems to have its first component as the cross product. So let's do the rest of the components, right? Let's set I equal to 2. Right, so that will be 2 JK, AJ, BK. This time I'm setting 2, so J and K can be only 1 or 3. So it's 2, 1, 3, A1, B3 plus 2, 3, 1, A3, B1. Is that clear? Okay, so now this is again, what is 2, 1, 3, right? So that's
minus 1.
minus 1, that's correct. So that's anti or countercyclic. So it's A1, B3, and this is cyclic. So that's A3, B1. And that's indeed your second component of A cross B. So these two work. Now let's immediately get the third one also. So it's 3, 1, 2. Three, 1, 2, that's 1. Right, that's also correct. So what we have is that whenever you have A cross B, this has 3 components. So notice this is a certain way of writing cross product. It has 3 components. So that's, you would say this is the 3 components. This means the first component of A cross B, second component of A cross B, third cross. So there's a 3 pieces in there. And those 3 pieces, which is labeled using I, so I is called a free index, is given by epsilon I JK AJ BK. Notice I is special. I is a free index. That's the notation or language is I is a free index. J and K are called dummy indices. Why do you say it is a dummy index? Because it doesn't matter what I call them. They're anyway repeated. They have no meaning in it. So this is the same as epsilon I mn am bn. It doesn't matter what I call the dummy indices because anyway that's summed. It is 1, 2, 3. But I has a special meaning. It has to match the left hand side. Like once you have set I to be I on the left hand side, right hand side also has to be I. So that has a meaning. Free index means that it has to be balanced on either side. Okay, so I crossed my time, but let me close by saying what is, or let's begin by saying that how many components in this quantity? How many components? How many free indices?
Just one free indice.
Just one free index. I is the free index. J and K is summed over. And the next question is, what is this equal to?
Is that the
Got to be 0, right?
Got to be 0. Yeah?
And why is that?
Because the delta is, I'm sorry.
Yeah, go ahead. Sorry.
The delta is only 1 for repeated indices. But when the indexes are repeated, then the Levi-Civita is 0.
That's correct. So what Moses is saying, or even Khaled probably was trying to say the same thing, is that this survives when J is equal to K. And this does not survive when J is equal to K, right? That's contradictory statements. So one of them is always 0. If J is equal, if the indices repeat, then epsilon is 0. If they don't repeat, this is 0. So either way, they'll be 0. So they're always 0, right? Based on symmetry, you say this is anti-symmetry property of, so Levi-Civita is anti-symmetric in all its indices. Kronecker delta is symmetric under replacement of all its indices. We'll come and start using those things more next time.
So
Let's stop here.
epsilon ijk times epsilon ijk just be 6 then?
Good, good question. Okay, so I haven't told you that. Yeah, so yeah, that's not very obvious. What is that equal to, correct? That's a typical problem I ask in the exam. And we will do this next time, how we can calculate that. By the way, is that a vector or is it a tensor? How many free indices in this?
There's no free indices.
No free indices. So this must be a number then. And then the question comes, what is that number, right? Jordan suggests it is 6. But let's address that next time, okay? So that's correct. The answer is correct. That's 6. But why is that 6? Where did he come with that number? Right. So that's a correct answer. But we will try to motivate that. Okay. But I think at this time I won't be able to start on that. Okay, good. Let's stop here. How many of you have classes right after this?
Not me.
You? Michael?
No.
Okay, so in principle, we can go beyond the time, but I won't. I'll try to stop at the right time. Usually one or few minutes, I try to go this way, but not intentionally. Yeah, I'll stop at the right time. Okay, thank you for listening.
Thank you.
Enjoy.
Thank you.
Thanks.
Yeah.
Bye.
Bye-bye.
Bye.
Yeah. Enjoy, guys.
You too.
Thank you.
Thank you. So where are you from, Luke?